So we talk about the electric potential due to a charged particle, something similar to what we have done in chapter 21, chapter 22. So now we have another version for the electric potential. So using the definition in the previous slides, we have Vf minus Vi to be something like this. And for a single charge particle, we know that the electric field is always on the radial distance. If it is a positive charge, it is pointing outward, and if it is a negative charge, it is pointing inside. So it's always on the radial distance. So we know that E dot ds is nothing but E dr. So which means that the cosine theta is either cosine 0 degree, which is 1, or cosine 180 degree, which is -1, depending whether it's a positive or negative charge. So now we can imagine that the final at infinite far away, which has a zero potential at infinite far away, which is Vf is 0 and F should be infinite far away on the R axis, because for R axis in the center it is small r equal to 0, and R can only be a positive value, so it goes to positive infinity, but there are no negative value for R axis. So we assume Vf equals to 0, and then we substitute E to be 1 over 4 pi epsilon naught times Q over R squared into here, and then it will be, and then we assume that the potential here is V, so that we substitute all the stuff in, and then this is constant, so that we can factor it out from the integral sign, and then we integral dr over r squared, which is negative r, so that one of the negative sign cancel, and then we substitute infinity into here, which is 0, and then capital R into here. Maybe we can make it small r, and this is r prime, but it's fine. So finally we can see that this is there's a minus sign here, so that if we minus this term, so that we will also have a minus sign. So that finally V would be something like this, 1 over 4 pi epsilon naught Q over R. So that I suppose in high school you should have learned this, and then you may memory something like F equals to 1 over 4 pi epsilon naught Q1 Q2 over R squared, and E should be 1 over 4 pi epsilon naught Q over R squared, and V should be 1 over 4 pi epsilon naught Q over R, and later on you will learn U to be 1 over 4 pi epsilon naught Q1 Q2 over R, something like this. But actually it come from some integration. Maybe you have question why we assume Vf to be 0 and infinity, if we and Vi to be V at R. If we can change it, definitely we should get the same result, but it is very easy to make some mistakes. It should be very easy to make some mistake, and you turn out there's a negative side, but actually it may only due to your math is not good enough, maybe. So if you just assume Vf to be 0 at infinity and Vi to be V at R, then you have less chance to make mistakes, so that for this derivation here, we make this assumption, and then it will comes out a trivial solution. And if you just make it reverse, you can easily make some mistakes. here. And so if we have one charged particle, the electric potential due to that charge will be like this. If we have more than one charges, we can simply calculate all the electric potential due to different charges, and then we add all of them together, and that's it. Okay, I think I have ignored something here. There should be something like 1/4 pi epsilon naught here. I forgot to put it here. There should be this term. There should be this term. So the potential is the algebraic sum of the individual potential with no consideration of direction. So you may have question why we need to learn a lot of variable like the electrostatic force, electric field, and the electric potential. The point here is that we really care about the electric field itself. But here, if we have the electric potential, it is a scalar. It is a scalar. So the main difference between the electric field and the electric potential is that the electric potential is a scalar, so that you can add them together easily, at least easier than vector sum. Vector sum. In chapter 22, when you need to calculate the integration, you need to decompose the vector in somehow like x direction and y direction, and you need to calculate the sum independently, and then so it will be at least more complicated. So here we can have another variable called the electric potential, and then when we add them together, it's just a scalar sum. So it is easier because the electromagnetic this theory is built somehow like 200 years ago, around 200 years ago. So at that time we don't have calculator, we don't have computer. So for the scientists, they need to work hard on the math so that they can derive very complicated theory. For Maxwell equation, they established around in the middle of 19th century, around 1855 something, if I remember correctly. So a positive charged particle produces a positive electric potential. It is very trivial because these constants are positive. R is also positive. So if Q is positive, V is positive. If Q is negative, V is negative. So a positive charge produces a positive electric potential, and a negatively charged particle produces a negative electric potential. So it is a simple fact. So the figure here shows three arrangement of two protons. Arrangements according to the net electric potential produced at point P by proton greatest first. So it asks you about the potential at point P. So given that the red dots are protons, which means they have a positive E charge amount, positive 1.6 times 10 to minus 19 Coulomb. So, so this is small d and capital D. So which one has a largest electric potential? Anyone can tell me? largest potential at point P. Which one?选择题反而更难吧。A、B、C。答案是他们是一样的。Yeah, actually they're the same. They should be the same because we need to do with the algebraic sum, so that you can know that this one and this one should be the same, and this one should be the same, and this one should be the same, so that when the two terms add together, they should give the same result. When you consider it in a vector point of view, if you consider the E field at point P, they are at the same direction, so that it should be the largest one, and this is the smallest one because most of it are cancelled, and this one somehow like this, so that it should be point to that side. So for electric field, this one is largest, this one is second, this one is smallest. But for potential itself, it is a scalar, so that when you add two terms which are equal, the term related to the small d should be the same, related to the large d are also the same, so that when you add together, all of them should be the same. So here the answer should be, they are all the same. Okay, so we have a sample problem here. So what is the electric potential at point P? located at the center of a square of point charge. The distance d is 1.3 meter. Charges are Q1, Q2, Q3, and Q4. Yeah, we need to calculate the electric potential in the center of this square. So we have Q1, Q2, Q3, and Q4, which has different charge amount. Some are positive and one of them are negative. So you already can see the answer is 350 volt. But actually, we need to write out the steps. Yeah. So in the quiz, you are suggested to write more steps, because if you make mistake at the end, then I can give you some points in between. If you just write something out and then you just write out a wrong answer, then you definitely cannot get many points. So now we know that d is the sine of the square, so we need to calculate r. R should be d over square root of 2, which is some simple geometry. So this is a right angle triangle, so that it should be d over square root of 2, which is very trivial. So V should be summation I equals to 1 to 4 VI, which will be 1 over 4 pi epsilon naught Q1 is 12. Q1 is 12. Well, all over, yeah, actually all over R, which is D over square root of 2. I can just factor it out because all of them are out. All of them are out. This is also out. This is also out. So all the R's will be factored out. And Q1, so we have nothing but Q1 plus Q2 plus Q3 plus Q4. So we just factor Q over square root of 2 out. So this is 8.99 times 10 to the 9th power, and then divided by D. What is D? Is 1.3. 1.3 over square root of 2, and then this one is 12. Q2 is negative 24. Q3 is 31. Q4 is 17 times 10 to minus 9. 10 to minus 9. So you need to remember the metric prefix. What is nano, pico, femto, micron, something like this. What I've mentioned last time. So finally, the answer should be 350 volts. 350 volts. And actually, on this graph, you can see that this is positive, this is positive, this is positive, this is negative. So you can imagine there should be a equal potential surface somehow like the yellow line, somehow like this, because this is the only negative. This is the only negative, so that it may be somehow like this. Maybe, but I'm not sure. Maybe it's a correct one, but don't ask me why it will look like that. Maybe you need to calculate many points and then you connect them together so that you get this dotted orange line. But actually, you can imagine somehow like this group is positive charge, this is negative charge, so that the electric potential is somehow like this way, decreasing in this direction. This would be the most negative electric potential, which will be minus infinity for here, positive infinity here, positive infinity here. So it is something like this is a peak of a hill, so that if you draw out the equal potential surface, it would be somehow like this. Somehow like 3 mountains here, and then that one is very steep, going to the negative infinity. Because you can imagine for this one, if you just plug in R to be 0 plus, this will be infinitely large. This will be infinitely large if Q is positive. If Q is negative and R is R plus, then this will be negative infinity. So you can imagine very close to this positive charge, the potential here will be very high. This will be very high. This will be very high. And this will be very low. So you can imagine like this. And there may be some potential, equal potential line, equal potential surface like this. So this is another sample problem. So there are 12 electrons of charge negative E are equally spaced and fixed around a circle of radius R relative to V equals 0 at infinity. what are the electric potential and electric field at the center of C of the circle due to these electrons. So actually, we can calculate it easily because the only thing we need to calculate the total electric potential is just to sum all of them together, 12, and Vk, which is 1/4 pi epsilon naught times negative 12e all over r. So it is very trivial, very trivial. Yeah, and for the next one, if the electrons are moved along the circle until they are non-uniformly spaced over a arc 112 degree, then what is the potential at C? How does the electric field at C change it? Or actually, it doesn't really change because we only deal with the electric potential, which is a scalar. So we still add all of them together too, so that we'll get the same result. So the electric potential doesn't change. They should be the same. But if you consider the electric field at this point and at this point, then they are different. And usually, in some of the selected problem, you may see v equals 0 at infinity frequently appear. It is actually a assumption. This is actually assumption because when you derive this equation, we also make this assumption, so that you can imagine if you plug in r to be infinity here, then this one will be 0. This one will be 0. Actually, this doesn't necessary to be true, because you can imagine in a mechanical problem, you can actually define u to be 0 here, and then this one will be, this one is h, so that here will be u equals mgh. But actually, you don't necessarily define u equals 0 here. Maybe you can define u to be 100. I don't really know about the potential, the SI unit, maybe 100 something. Then this one could be 100 plus this mgh. And actually, if we consider the conservation of mechanical energy, and if U plus K initial equals U final plus K final. So if this one is mgh, this one is 0, it is the same as we have mgh plus 100, this one plus 100, then we can just cancel it out, so that we can just make this one u equals to a Pikachu, then it can be fine, and this one can be mgx plus a Pikachu, then it works fine. So it's same case as here. If you just assume v to not to be a 0 at infinite point, then we will add some stuff here. So it makes this equation not so elegant, not so elegant. So usually we'll assume v to be 0 at infinity far away. So the next one, we consider the potential due to the electric dipole. The electric dipole. So we have learned it in chapter 22 and 23. So we know that the dipole is nothing but the q times the distance vector. So the distance vector d should be pointing to from the negative charge to the positive charge, and the magnitude should be the distance between them. Q is the charge on each side, and they should have a negative sign. They should have a equal magnitude but negative sign, but opposite sign. One is positive Q, one is negative, another one is negative Q. So for calculating the electric potential at a distance, we can just add them together so that we can do some algebraic calculation. And now we consider a point not actually on this z-axis. It is somehow with an angle theta with the z-axis. So that actually here we can draw a line like this. We can draw a line like this, which is perpendicular to this r plus and r minus. Also, we assume that this point is quite far away. If we assume this point is quite far away, we can assume this line and this line are parallel to each other. If it is very close, then you can see that they are not parallel to each other. But it is very far away, just like you can imagine the sunlight coming to the Earth is parallel ray. So here we also assume that this point is far away. This point is far away, so that we can regard r plus and r minus. These two is parallel to each other. So in this case, we can draw a perpendicular line here, and then this r minus r plus is this one, which is d times cosine theta. So we have a approximated equation like this. And also r plus times r minus should be r squared. We assume that they should be very close. So in this case, we can consider because this is infinitely far away, so that the whole term should be approximately the same, which is r. But when we calculate the difference, we cannot consider they are the same, because if we just consider it's the same, r minus r plus should be 0, and then there is nothing left. So we make this as approximation, so that r minus r plus should be d cosine theta, and r plus times r minus should be r squared, and then we can substitute it into here for the denominator and the numerator. And finally, in the denominator it is r squared, and the numerator it is d cosine theta. So we can merge QD, which is the dipole moment, T cosine theta, like this. So it is nothing special. Yeah. So up to now, we consider the charge, which is discrete charge. We can count it one by one, so that we can use this equation to add all of them together. So we can calculate one by this equation, and then if we have 10, we add 10 terms together. If we have 100, we add 100 terms together. So the next one is if the charge distribution is continuous, not discrete charge, then we need to use the integration to do all this stuff. So actually, V is integral of dV. We calculate all the small dV, which is generated by some small charge packet, and then we integrate all of them together in a volume, because it would definitely be a three-dimensional space. The charge will distribute something here and something there, and then we separate into, or maybe it's in a sphere, so that we can separate into many parts, and then we calculate them one by one, and then we integrate them together, not by summation. We use the integration to add very small packets. So finally, you become dq over r, because it's usually related to r, and this term is a constant, so that this one will look like this. Equation 22.32 is look like this, and if you are given the dq, which is a formula of r, then you can do this integration to find the overall v.